Okay. And chapter 6. There we go. Okay, there we go. So chapter 6 is called Chemical Reactivity and Mechanisms. So if you kind of skimmed through this chapter or looked at it at all, it definitely has a lot of review stuff in it. And it's review stuff from second semester general chemistry. So like the kinetics and thermodynamics stuff. We're going to kind of fly through that. And it's not because it's not important. It's partly because it's review, and then partly because we don't really need to know the details that you needed to know in general chemistry. We will definitely spend more time on the things that we do need to know. But for the most part, for like the first 10 slides or so, it's just going to be a little bit of reminders of what you saw last semester. Let me adjust my video. There we go. So, and a lot of this is going to be reminders on vocabulary, like enthalpy. This little thing up here. So enthalpy is really just another way to say the energy associated with the reaction, but we write it as delta H or Q. It's also just referred to as heat. And technically the energy that's being transferred is kinetic energy. So all of those things mean the same thing, which I know does not make it easy to learn or remember, but unfortunately that's just the way it is. One of the ways, well, okay, let me take a step back. In general chemistry, you learn how to calculate delta H all kinds of different ways. And one of the ways is by calculating how much energy it takes to break a bond, how much energy is released when bonds are formed. And this is the standard, under standard conditions. Remember, that's what the little knot means, is that we're under standard conditions. There's two main ways to break a bond: homolytic and heterolytic. So we know homo means same, hetero means different. So how that applies to these terms is how the electrons are being distributed when the bond breaks. So if a bond breaks, those electrons have to go somewhere. And in a homolytic bond cleavage, we're treating the two atoms that had the bond the same. So when, let's see, let me get a different color here. When this bond right here is breaking, it's made up of two electrons. Each electron is going to go to one of those atoms. So the X gets an electron, the Y gets an electron. And notice the arrows that are there, they look like this. This is called a fishhook arrow. It only has the single side on it. So it has that single side on it to show us that that's the movement of one electron. When we go through a homolytic bond cleavage, we will always make radicals. A radical is an unpaired electron. So there's our X and our Y radicals. This is the less common of the two options. We actually have an entire chapter dedicated to radical reactions, and that's really the only time we see them. So by the time we're done with organic chemistry, we'll cover 24 chapters, I think, and only one of them goes with radical reactions. So it does happen, but it's definitely the minor option. And then the other half over here, heterolytic, so it's telling us that the two atoms get treated differently. So in the bond that's breaking, this little guy right here, notice the arrows going from the bond onto the Y atom. So that means both of those electrons are going to go onto the Y atom. And when that happens, we're going to make ions. So because the electrons went onto the Y atom, our Y is our anion because it gained those electrons. And the X is our cation because it lost the electrons that were part of the bond. And then the arrow that goes with this one is a regular two-sided arrow, but we do refer to this as a curved arrow. It's also sometimes called an electron pushing arrow. I'm going to put it up here also. I ran out of space. And then one more name for you. It's also just called a mechanism arrow. Curved arrow is probably the one you'll hear the most. I kind of combine them. I'll often call it a curved mechanism arrow just to kind of put as many words in there as possible to have you understand what I'm asking for in terms of like a test question. Sometimes I'll even put curved mechanism arrow and then in parentheses electron pushing arrow just to kind of hit anything in your brain that will help you understand what I'm asking for. Okay, so those are our two main types. We're definitely focusing on the heterolytic side because that's what most reactions go through. A little bit on energy diagrams, and we're definitely going to look at this later on in the chapter 2 in a few slides, but we can tell a lot of information about a reaction from the energy diagram. The reactants are at the starting point. The products are at the ending point. This graph is specifically looking at enthalpy, which means we're looking at the change in energy from the reactants to the products. And if our products are higher in energy than our reactants, endothermic. And if our products are lower in energy than our reactants, it's exothermic. So this is only looking at the start and the finish. Enthalpy or thermodynamics focuses on where we started and where we ended. It doesn't look at the middle at all. Kinetics looks at the middle. Entropy, this is one we're going to fly past, but entropy is a measure of disorder. So if we go from 1 mole of reactant and it breaks apart to make 2, we're increasing the disorder, we're increasing the entropy. And an increase in entropy usually means that a reaction is spontaneous or that it will happen. When this comes up in later chapters, I'll refresh your memory on this. It's not a big thing for us though. When we talk about delta H, when we talk about enthalpy, another way to look at that same energy change is Gibbs free energy. And Gibbs free energy is now taking into account entropy. It can be confusing because we're looking at the same part on the graph, but what's different is what's on that y-axis. So even though the graphs look the same, they're not technically the same. So this is looking at kind of a bigger picture and incorporating some more information, but we're reading the graphs the same way. We're looking to see if energy is being released or if energy is being taken in. It's just different types of energy. A lot of the reactions we look at are in equilibrium. So we have a reversible reaction that can go from products to reactants and vice versa. And this is showing us that wherever we reach our equilibrium, that's when delta G will be at the lowest. So you probably looked at graphs like this last semester. You definitely looked at equations like this last semester. But this is telling us that as we're doing this equation, A and B are making C and D. These are the concentrations down here. So in the beginning, this would be the very start of the reaction, we only have A and B, which means the reaction's going to go really fast. But as we make more C and D, the forward reaction slows down, the reverse reaction speeds up. Eventually, we reach equilibrium. And we know that equilibrium doesn't mean equal. Equilibrium means that the concentrations have stopped changing. And so wherever we reach the bottom of that curve, that's where we've reached equilibrium. So really the most important thing on here is it's telling us that the energy is at its lowest when we've reached equilibrium. And that will be a specific ratio of reactants to products, or products to reactants technically. But most importantly, the energy is at its lowest. We know low energy means a high stability in chemistry. Okay, so we talked about the start and the finish of these graphs. The middle part of the graph is kinetics. How fast does the reaction happen? So thermodynamics is an energy thing. Kinetics is a speed thing. Again, I know you've dealt with all of this last semester. We don't do it. We're going to kind of use the terms first order and second order to describe reactions that are happening, but we're not doing any math with it. This stuff's important down here. We know that how fast a reaction happens is determined by these three things. Do I have... Okay, I do. I couldn't remember if I had a slide for each one or not. I have not been turning pages in my own notes. That might help me. So we're going to go through these. We're going to go through these three things. So the first thing that will affect how fast a reaction happens is the activation energy. And this is the biggest one for us when we're looking at a graph. The activation energy is abbreviated as a capital E with a lowercase subscript A. So energy activation, I guess it's kind of how you could think about it. This is the definition of it. It's the amount of energy needed to create the reaction. So when two molecules run into each other, it has to be enough energy to break the old bonds and create the new bonds. If they just kind of like skim past each other, that's not going to result in a reaction. So it has to be a hard enough collision to make that happen. Sorry, my notes keep falling over. Let me just move this thing. Okay, there we go. We can see how big the activation energy is from a graph. So I often just kind of refer to this as the hill. So if we have a small hill, that means that it's going to be a faster reaction. And a small hill or a small activation energy means that we're going to have a large K value. So remember that lowercase k is the rate constant. It's what's in the rate equation. Again, we're not doing the math here. We're just talking about it conceptually. And then the other graph example, we would refer to this as a larger hill, which means that it's going to be a slower reaction. Now, knowing whether a reaction is fast or slow just by looking at the graph, we can't really know that, but we can compare them. So we can say that the one on the right is a slower reaction, the one on the left is a faster reaction. But if we only had one of those graphs, we couldn't say whether it was a slow or fast reaction because those are relative terms. Those are comparison terms. So this is usually a comparison thing. If you were given 4 graphs, you could say which reaction's the slowest, which reaction's the fastest, based off of the height of those hills. But just one reaction, you could say this is the activation energy, but you couldn't really use the words slow or fast to describe it. So that's the first thing that affects the speed of the reaction. The second is the temperature. The higher the temperature, the faster the reaction. We're giving those molecules more energy. That means they can run into each other faster. So that means that more of the collisions will have enough energy to overcome that activation energy. Another way to say that, another way you may have heard it, is that if we have a higher temperature, then more of the collisions will be effective collisions, which just means that it will go through the reaction. Chemist's rule of thumb is that for every 10 degrees we increase a reaction, the reaction rate doubles. So 10 degrees isn't a big difference, especially if you're trying to heat something to 100. It's actually kind of hard to keep it at constant temperature. and getting it to 110 on accident is fairly common. But having that small temperature change does make a big difference. So higher heat, higher energy, faster reaction. And then our last one is geometry and sterics. So this really just means that our molecules have to run into each other in the right way. So sometimes this is referred to as orientation. Kind of depends on what book you had. It doesn't really have like a specific name, just kind of it's how we describe it. But in this example, we have these two molecules that are going to create these diatomics. So a blue and a red together and the greens together. So in order for this to happen, we're shown two collisions that are ineffective, meaning if those molecules run into each other, blue to blue or blue to green, nothing's going to happen. They're just going to bounce off of each other. But if the molecules run into each other, green to green, then those green molecules can form that green-green diatomic, and then the blue and the red ones will create the other molecules. So all of this picture, all of this is telling us that we have to have the molecules run into each other in the right way with enough energy in order for us to have a reaction. How this affects the speed is if they have to run into each other in a very specific way, it's going to be a slower reaction because less collisions are going to do that. But if it's just two atoms and they could run into each other any kind of way, then it's going to be a faster reaction because it's not as specific. So the more specific the collision has to be, or the more precise it has to be, then it's going to be a slower reaction. And the more generic it can be, the faster it will be. Questions at all about this? I know I'm going kind of fast. Okay.
Can you repeat what you said about it being more precise?
Yes. So if a collision needs to be more precise, so I would consider the example on the screen here that it needs to be pretty precise, then it will be a slower reaction. And if the atoms can run into each other in any way they want, and it still results in a reaction, then that's going to be a much faster reaction.
Thank you.
You're welcome. Okay. Another thing with kinetics that we can affect is a catalyst. So the picture that is up here, we have two energy diagrams. The blue is without a catalyst. So we can see that activation energy, that hill is pretty tall. And then when we introduce a catalyst, when we add a catalyst into the reaction, the activation energy is much smaller. One of the differences here, though, is that our reaction went from having one hill to having three little hills. So that's how many steps the reaction takes. We'll look at that in a couple slides, I think. But that's telling us how many steps. So a lot of times a catalyst will introduce extra steps. But because that activation energy is smaller, it's going to be a faster reaction. So here's our definition of a catalyst right here. A catalyst will speed up the rate of reaction without being used up. So what that means is that when the reaction's complete, we've turned our reactants into products, but we still have that catalyst. Now, sometimes that means it can be reused. Sometimes they can be regenerated or recycled. Sometimes it means they're just garbage at the end. But when we say it's not being used up, it means that it's not part of our products. It is utilized in the process, and then we're done with it at the end. The way that it speeds up a reaction is that it lowers the activation energy. Technically, there are catalysts that are called negative catalysts, and they actually slow a reaction down. They're not very common. They're not used very often. But sometimes if you're doing research and if a reaction's going really fast, but you want to have time to do changes with it, you actually want to slow it down. So a negative catalyst can actually be used, and then it will hinder the reaction. It will add more barriers, and it will make that activation energy taller. So when we use the term catalyst, we are referring to something that's speeding up a reaction. And if we want to refer to the other one, it would always be called a negative catalyst. We have catalysts in us all the time. Enzymes. Enzymes are a specific type of catalyst. They are naturally occurring. So this is this giant molecule here. This is amylase. So it turns starch into sugars in our body. So this is what a biochem molecule looks like. So you can see like tiny little rings over here, or even just the little zigzag shapes that are in the middle there. The red, you can see tiny little red atoms. Those are oxygens. And then the little blue ones are nitrogens. The rainbow ribbon in the middle, the curly Qs are beta helixes. This is from hydrogen bonding or dipole-dipole interactions. So let me switch colors here. Maybe blue will stand out. So like if we had a molecule right here and a molecule right here, or not a molecule, sorry, that's the wrong word choice. If we had a functional group in each of those positions, they're going to be attracted to each other through dipole-dipole forces. And so it causes that curly shape to maximize the attractions. And then the ones that look like this over here or down here, those are called, oh, I think I used the wrong phrase. The first one's alpha helix. These are beta pleated sheets. I think I switched my alpha and beta the first time I said it. On a beta pleated sheet, it's kind of the same thing where there's a dipole-dipole attraction, but it just kind of causes them to line up in a little row instead of doing this curly Q. So whether they do one or the other depends on what those functional groups are and how far apart they're spaced. So biochem next year, you'll learn a lot more about this. But these molecules are gigantic. So biochemistry is really just organic chemistry intensified in terms of size. I was talking to another teacher about biology because I know no biology, but I find it very interesting. I was saying that I wanted to take her class and learn more about biology. And she said that I should. And she said that because we're just sacks of organic molecules. And I thought that was the strangest way to describe a human body, but somehow it made me want to learn more about biology. So she knew how to get me. All right, this is second semester general chemistry in one slide. Reactants, products. So the reactants are always on the left of our energy diagram. The products are always on the right. So notice the way these are labeled. Our y-axis is potential energy, which is really just a super generic way to say the energy associated with everything involved. Reaction coordinate is the x-axis, which doesn't really have a meaning. Sometimes we kind of refer to it as like the time progression of a reaction. Sometimes it just says reaction down there. So really it's just showing us the change going from reactant to product. Kinetics is the middle of this graph. It's the activation energy. It's the speed of the reaction. And thermodynamics is the energy difference between the starting point and the ending point. So thermodynamics are the start and the end. Kinetics is the middle. That's second semester general chemistry. That's all it is. Okay. Last slide in this little section here. We talked about steps when we looked at the catalyst. The number of hills is the number of steps of a reaction. The steps is referring to like how many times bonds have to break. So we don't normally have a reaction where we break one bond and the reaction's done. It normally kind of has to go through what are called intermediates in order to go to a complete product. So at the tops of the hills, these are transition states. So these are the highest energy positions, which means that they're not stable at all. And when we have a transition state, we have partial bonds. So this means we're at the point where the bonds that are going to break are kind of halfway broken, and the bonds that are going to form are halfway formed. It's in transition. It hasn't quite switched into the new thing yet, but it's also not the starting thing either. It's in transition. It's in the middle. The intermediates are in these little valleys, and the intermediates are the products from each middle step. So this is a 3-step reaction. So this would be the product from the first step. This is the product from the second step. And then the third step would give us our final product. When we are creating those intermediates, that one's the product from the first step, but it's also going to be the reactant for the second step. So we are using that intermediate to continue on. I think, let me check. Oh, I think I have a little, okay, yeah, one more in this zone, and then we're gonna move on. The last one, which you probably didn't talk about in general chemistry, is called the Hammond postulate. And the Hammond postulate tells us what the transition state will look like. And so this means we know that the bonds are going to be kind of half broken and half formed. And I use the word half, but it's not really an equal point. The transition state is going to look closer to whatever it's more similarly like energetically. If we're looking at the graph, that we could also just think of it as it will look like whatever it's closer to physically. So when we have an exothermic reaction, our transition state is closer to our reactants. They're closer to each other in energy. They're closer to each other just in distance on the graph. So that means that our transition state is going to look like a reactant. So as the bonds are breaking and the new bonds are forming, we could think of this as the new bonds have only formed maybe a quarter of the way, and the old bonds have only broken a quarter of the way. So it's much closer to being a reactant. When we have an endothermic process, the transition state is much closer to the products in energy and in physical distance on our graph. So that means that our transition state is going to look like a product. So meaning those new bonds are maybe 3/4 of the way formed, and the old bonds are 3/4 of the way broken. So it's almost finished, whereas with the exothermic, it's just getting started. If we had a graph that looked like this, there's our transition state. So the reactants and the products are at the same energy level. With that type of graph, our transition state would be at that halfway point. It's halfway between the products and the reactants energetically and distance-wise. So that means the bonds would be half broken and half formed. This concept, it comes up occasionally. We use it to kind of describe why some things are happening, but it's not going to come up a whole lot. So that means that when it does come up, I'll definitely remind you of what the Hammond postulate is, just because we don't talk about it enough for it to stick in your brain that well. Questions at all about this?
Will this be common in future chem classes?
The Hammond postulate?
Yes.
No, this is definitely an organic thing. Yeah. Anything else? Okay. So this kind of takes us to the bulk of this chapter. So our chapter title was Chemical Reactions and Mechanisms. So we're going to be looking at how chemical reactions happen from an organic chemistry point of view and how we show that with mechanisms or electron pushing arrows. So we're starting by defining two new words for us, nucleophiles and electrophiles. Now these two words we are going to use pretty much in every single chapter from here on out. And understanding what the words mean and understanding how to recognize them is definitely going to be important. Most reactions that we talk about could be categorized as a polar reaction. That means that there's an attraction between something negative and something positive. And that negative and positive could be a full negative ion and full positive ion. But for organic chemistry, it usually means partial negative and partial positive. So either one of those will work. It just has to have that opposite charge attraction. And notice it's telling us that this could be from the reactants, the intermediates, or the products. There just has to be some type of attraction in there. We know negative attracts positive. We know that there's that opposite attraction, which means that something that's electron rich, which would be the negative thing, is going to be attracted to something electron deficient, meaning it just is lacking electrons. So that's the positive thing. A couple examples down here. This is a CH3Cl molecule. So there's its little Lewis structure. We have a carbon bonded to 3 hydrogens and a chlorine. This is a polar molecule. And it's polar because that carbon-chlorine bond is a polar bond. And so it's creating a dipole moment, not just for the bond, but for the entire molecule. Because of that, the carbon is partially positive. So this is a polar molecule. That little red arrow there, remember that's our dipole moment. And so we have a partial positive on that carbon. The chlorine's the partial negative, but this is organic chemistry, so we focus on the carbons. So the carbon is partially positive, which means that our carbon is electrophilic. Do you remember what the suffix philic means, or phile?
Loving?
Yeah, so that tells us that this carbon loves electrons, or it's attracted to electrons. So when something's an electrophile or electrophilic, that means that it's going to be partially positive or positively charged. And it means that it's going to be attracted to things that are negative or partially negative. We can see that in our little diagram here, our electron cloud picture. So the red is the negative chlorine. Wow, let me put that as a partial. Let me be a little more. One more time. There we go, partial negative chlorine. And then the greenish area is that partial positive carbon. So this is telling us that when our carbon is bonded to chlorine, it's going to be an electrophile because that chlorine is electronegative and pulling those electrons away from the carbon. On the other half over here, we have a carbon that's bonded to 3 hydrogens and a lithium. So lithium is going to be less electronegative than carbon, which makes our carbon the partially negative atom in this structure. So this is still going to be a polar molecule. It still has a dipole moment, but notice the direction that that dipole moment is drawn. It's going towards the carbon because carbon is more electronegative. Carbon is more electronegative than lithium. There's not a whole lot of things we use that are less electronegative than carbon. In terms of non-metals, carbon's is pretty much as low as we get. So in order to get something that's less electronegative, we do have to switch over into the metals. So lithium gets used for this, magnesium gets used for this. We'll see that in a few chapters. Because of that, carbon usually isn't the thing that's partially negative. Carbon is usually the thing that's partially positive. So methyl lithium does exist. We will use it, but it is definitely used less than having a carbon that's partially positive. So in this example, though, because carbon is partially negative, the carbon is our nucleophile, or it's nucleophilic. So that means that it loves the nucleus, which is where the protons are. So something that is a nucleophile is partially negative or just negative, and it's going to be attracted to the nucleus, which is where our protons are. So most reactions are going to happen because of an attraction between nucleophiles and electrophiles. Looking at my notes over here. Oh, one more thing I want to add onto the electrophile list up there. So for our electrophiles, I listed it as something that's partial positive, something that's positive. Something else that fits into that category is an atom that has less than an octet. So it can take on those extra electrons. It might not necessarily love those extra electrons, but it does have the space for them. We don't see this as often. Boron and aluminum are the ones that come up. We talked about those with being Lewis acids, and it's kind of the same idea here. So it comes up occasionally when we use metal catalysts, but definitely not often. Okay, let me check our time. Oh, we're good. So a little bit more on each of these. Our nucleophile is something that is electron rich, so negative, partially negative, and it can donate a pair of electrons. So these also fall under the category of a Lewis base, because that's a Lewis base definition, is that they are electron donors. There's some examples down here of things that are nucleophiles or things that are electron rich. So we have our partial negative carbon that we talked about on the last slide. We have a negatively charged oxygen, so this is ethoxide. We have our ethanol here. In this, oxygen is partially negative just because it's more electronegative than carbon. So it's the electronegative atom in that molecule. And then the one that might not seem like it fits is a pi bond. Pi bonds fall into this category just because it's an abundance of electrons in one space. Pi electrons, because they're above and below a molecule, are easier to react than a sigma bond. Sigma bonds are between the two nuclei, and so it's going to be a stronger bond. The pi electrons, because they're above and below, are going to be easier to break those bonds or react those bonds. And so it makes that an electron-rich area or a nucleophile. When something is more polarizable, that means it's a stronger nucleophile. So when we think of whether something is polarizable or not, we're usually referring to size. So if we can think about like moving electrons around that electron cloud, how easily can we push the electrons to one side to make a stronger charge, whether it's a partial charge or a full charge. This distinction doesn't come up very often because we're generally using that first row of the periodic table, carbon, nitrogen, oxygen. We don't deal with a whole lot of larger atoms. So this is definitely a true statement, but it's definitely a minor part of this. Electrophiles then. Our electrophiles are electron deficient species. partially positive, fully positive, or less than an octet. They can accept a pair of electrons, which means that they are technically Lewis acids, because that's our Lewis acid definition. Carbocations definitely fall into this category. So a carbon with a positive charge, and partially positive atoms fall into this category. Our carbocations are positively charged, but they also do technically have less than an octet. That's why they're positively charged. So they kind of are checking two boxes there. And then something like boron, so BH3, this has less than an octet. So I'm just going to put less than 8. And so it would fall into this category as well. It can accept that pair of electrons because it has the space. So we are, of course, focused on the carbon side of things, and those carbocations and those partially positive carbons are where we will see most of our electrophiles. We can get a partially positive carbon anytime it's bonded to a heteroatom. So a carbon that's bonded to a nitrogen, oxygen, or any of our halogens is going to be partially positive. And so that's where we will see that. Notice that none of these carbons have any partial charges. So carbons in general are actually kind of hard to react. We have an entire year of chemistry devoted to carbon reactions, but they're kind of difficult to react with. And because of that, we have to have something else that makes them a little bit less stable. So if we have a heteroatom bonded to them, it will create this charge that will then make them more reactive. So we have to have something that turns them into a reactive site or a reactive atom. When we just have carbons, bonded to hydrogens, nothing's really going to happen to them. So we have to have those heteroatoms in place in order for it to become reactive. This is a nice little summary table from your book looking at nucleophiles and electrophiles and some examples. So under that nucleophile category, we have inductive effects. So we used that phrase or that term when we looked at ARIO. So really just means that we have another atom that's affecting it. So notice that word is used in both of them. It's talking about electronegativity. So inductive just means it's affecting the electrons. So in one case, it's making the carbon partially negative, and the other one, it's making it partially positive. A lone pair can be a nucleophile source because we get that partial negative charge and then our pi bond. And then on the electrophile side, we have that empty p orbital, so our carbocation. And then something else that would fall in, well, we'll not put an empty p orbital, we'll just put less than an octet. So it's not technically a p orbital. Something like BH3. I guess it kind of, well, whatever. I was going to tell you that it is kind of a p orbital, but kind of, not really. It doesn't quite do the same thing. Okay, questions on electrophiles and nucleophiles?
So are we going to be applying this information like in the next section, or like how would you test this on this?
Yes. So this can show up in the test in a couple ways. One would just be if I give you a molecule, like give you this molecule and ask you, is this an electrophile or a nucleophile? So it could just be recognizing atoms or molecules as electrophiles or nucleophiles. But then how we're going to use it in our next handful of sections is looking at how nucleophiles and electrophiles react together.
Okay, and do we need to be able to identify like which feature categorizes it as nucleophiles or electrophiles, or we can just recognize them on our own? We don't have to like tell you why it is that way.
No, you wouldn't have to tell me why. You wouldn't have to use like inductive effect or lone pair or pi bond. You wouldn't have to use those phrases. You just have to say, this is a nucleophile.
Okay, perfect. Thank you.
You're welcome. Anything else before we move on? Okay. So there's a big blank space here because I'm going to do examples as we go through these. Okay. Sorry. We are going to look at mechanisms and arrow pushing. So we're looking at these, I did it right here too. These curved arrows, also called electron pushing arrows. Mechanisms show us how a reaction happens. So we've already looked at one type early, chapter 2, I think it was. We looked at acid-base reactions. So I'm going to draw an acid-base one here, just kind of as a reminder of what we've already seen and kind of a introduction. What we're going to look at on our next handful of slides, though, are these 4 main types of electron arrows. And we're going to go through each one. We're going to look at examples. These are the 4 main types of ways that reactions take place. Now, kind of a side note, reminder, warning, however you want to take this. One of the things that gives organic chemistry a bad rep is that people think that there's a lot of things you have to memorize. Starting next chapter, we're going to start looking at reactions. And then pretty much every chapter here on out is just reactions. One of the things we look at is if you mix this with this, it makes this. That's the reaction. But we will also look at the mechanism. So if you mix this and this, how do the electrons move around in order to get the product? You cannot memorize all the mechanisms. We will learn hundreds of mechanisms by the time we're done with organic chemistry, and you just can't memorize them all. They won't stick in your brain. You'll get them mixed up. It doesn't work that way. The students that try to memorize them are the ones that say that organic chemistry is really hard and have difficulties with it. Instead of memorizing them, you have to see the patterns. You have to learn them. You have to understand them. So memorizing them is kind of like the low level of learning. Understanding them is the next level up. In order to understand them, you have to know these things. So at this chapter, understanding these 4 types of arrows is going to be really important, and being able to see what's happening and know why it's happening is going to be super important, because we are going to apply these 4 types of mechanisms in every chapter from here until the end of fall semester. So this is probably one of the most important things that we will learn because of how much we're going to apply it. All right, there's my little disclaimer, my little warning for you. So let me remind you of what we've seen for a mechanism. There's my acid, my carboxylic acid. I'm going to react it with methanol. So this, I think this was a test question, or super similar to a test question. You had these 2 and you had to draw the products. The mechanism that's happening here, we know that this is the acid and this is the base. And we know that because of ARIO. We know that this is going to be a more acidic hydrogen than this one. They're both attached to oxygen, so the A is gone. But this is going to have resonance when it's in its conjugate base form. So the stronger acid is going to be the one that loses its hydrogen. So here's my mechanism arrow. I'm going to do it in, we'll do it in blue. We're going to start here, and we're going to go onto that hydrogen. That arrow is showing a bond forming between the oxygen and the hydrogen. Where your arrow starts and stops is important. Some of you lost points on the test because of your arrow placement. Some of your arrows were close, but not quite there. And so you might not have lost points, but you definitely got a little note from me telling you where they should have started and stopped. An arrow needs to start at an atom or a bond. It can't start like in between things. And for this one, we're using that lone pair on oxygen to form a bond to the hydrogen. So we're starting on the lone pair, we're ending on the hydrogen. This kind of goes along with what I just said. We can't memorize where bonds start and stop. We have to understand what's happening. When an acid-base reaction happens, we are removing a hydrogen from the acid and adding it to the base. So in order to form that new bond to the base, we're using that lone pair electron, we're reaching out and grabbing that hydrogen. That's not the only arrow we need in this though. That hydrogen can't be bonded to both oxygens at the same time. So we're going to draw one more arrow. We're going to start at that bond and end on that oxygen. And this is the bond breaking. And so what we get from this is that. So this would be the conjugate base, and this is the conjugate acid. We've removed our hydrogen from our acid, we've added a hydrogen to our base, and we've created our conjugate base and our conjugate acid. So our conjugate base has an extra lone pair on it. That's because the bond, the electrons in that bond, are now a lone pair on that oxygen. And our base, now our conjugate acid, has that extra hydrogen bonded to it. And we used, let me draw that one out just so you can see. Oxygen normally has two lone pairs. We used one of those lone pairs to create that bond. So understanding formal charges and whether or not we would have one lone pair or two lone pairs is going to be really important. Even if we don't show those lone pairs, we need to understand that they're there. All right, we're going to go through these four things. First is nucleophilic attack. So it sounds kind of brutal. We use the word attack, but a nucleophile attacks an electrophile. So another way to say it is that a nucleophile is bonding to an electrophile. I think we use the word attack in this case because then we're using the electrons from the nucleophile to make that bond. So here's a description of how the arrow looks. The tail of the arrow, or the start of the arrow, is starting at the electrons of the nucleophile. And then the head of the arrow, where it ends, is ending on a nucleus. So at the atom of the electrophile. So in this case, we have a bromide ion as our nucleophile. Our arrow is going from the lone pair to that atom, that positive charged atom. This arrow is showing a bond forming. And so right here, I'm going to color it in. That new bond right there, that is from the result of that arrow. I'm going to do one more example on the bottom there, but questions about this first example?
Does it shift like that all the time when you add that electron pair?
What do you mean, does it shift? What shift?
Like, because like right now it's, you know how like the actual electrophile has that bond going straight up, and then it shifts to the right side and adds that bromine.
So a
Would
lot
that
of
always
times we
happen?
do draw it a little bit different. And part of that is a geometry thing. So when a carbon is positively charged, it's trigonal planar. And then at the end of this reaction, it's tetrahedral. So it doesn't necessarily have to be. I mean, if we left the carbon bonds like that and then just drew the bromine off to the side, that would be completely correct too. It's not the best representation of the bond angles, but it is showing that new bond in there. So how they're placed on there isn't really a big part of it. Was the previous example? Yes. So there was a question in the chat asking if this previous example was a proton transfer. So this one, and it definitely is. So that is an example of a proton transfer. Okay, I'm going to draw one more down here just to show you one more example of a nucleophilic attack. So I'm using another carboxylic acid, and I'm going to use methanol again too. Because sometimes these molecules react with each, oh, no, that's not what I wanted to hit. That's not what I wanted to hit either. There we go. Sometimes they react with each other in different ways. I just want another electron down there. The PowerPoint controls are right next to where I'm trying to draw. We're going to put it right there. Okay. In this reaction, my carbon is partially positive and my oxygen is partially negative. So my carbon, my partially positive carbon, is my electrophile, and my partially negative oxygen is my nucleophile. So here's our arrow. We're going to start at the lone pair of our oxygen, at the lone pair of our nucleophile, and we're going to end at that partially positive carbon. Now, sometimes when we do a reaction, we only need one arrow, like in the first example, and sometimes we need two arrows. In this case, we need two arrows because if we stopped right there, I'm going to draw a really ugly structure, but if we stopped right there, we would have a carbon that has 5 bonds. We can't have a carbon with 5 bonds. So, erase my ugly, ugly structure. We're going to do an arrow from the pi bond onto the oxygen. Now that's technically not a mechanism arrow. That actually falls into our resonance patterns that we saw. That's a pi bond between two atoms of different electronegativities. So we add in resonance arrows to help the flow of electrons. So this is what we have. We have a carbon in the middle that is now bonded to our oxygen. And our oxygen that was doubly bonded now has a single bond with a negative charge. We're going to keep using the same example on the next slide. So actually the next couple slides. So this would not be a finished product. It has charges. We will keep going through the mechanism for this reaction and use this. But so this isn't a finished thing, but it is showing an example of that nucleophilic attack. The charges have to stay consistent. So you've heard me say that for a handful of different things, but it's true here also. We started with an overall neutral reactant. Both of our reactants are neutral. Overall, our product is also neutral. We have a negative oxygen and a positive oxygen. So overall, it is a neutral substance. Questions on that first one? Okay. number 2. Number 2 is called the loss of a leaving group. Oh, and let me go back up one slide. So I used this in my example, but also notice it's abbreviated. Abbreviated is just NU, and this one I have a little abbreviation of LG. As we look at bigger examples, I will use those abbreviations to label what kind of step is happening. When a loss of a leaving group happens, that means that something's leaving. I mean, it goes with the name. But how that happens is a heterolytic bond cleavage. So that means that an atom or a group of atoms takes an electron pair with it and leaves. So here is our starting reactant. That arrow is showing the bond breaking between the carbon and that bromine. The bromine is our leaving group because it's the one that's getting the electrons. So as that bond breaks, we're showing the electrons from the bond move onto that bromine. Because those electrons move onto the bromine, our bromine becomes negatively charged. So bromine is negative because the electrons moved from the bond to the bromine. And as a result, we make a carbocation because our carbon lost those electrons that were making up the bond. So our carbon is positively charged and our leaving group, our bromine, is negatively charged. Overall, we still are neutral. Neutral to start with, positive and negative to end with, so overall neutral. Also, a little side note to point out, notice what we just looked at on the top here and what we looked at on the next slide. It's an opposite reaction. They're in equilibrium with each other. This is going to happen often. So those two reactions are in equilibrium with each other, but that does tell us that a nucleophilic attack and the loss of a leaving group are opposites from each other. And one of them, a nucleophile, is bonding to an electrophile. And in the loss of a leaving group, a nucleophile is leaving from an electrophile. So two halves of what's going on. The other example that's over here has a lot of arrows, but there's actually only one arrow that's showing the loss of a leaving group. So if we look at this reaction and we draw in the final product, I'm going to start up at the top because nothing's happening to that oxygen on the left. The oxygen on the right, this arrow is showing that we're going to take that lone pair and make a double bond to that nitrogen. And then we did have a double bond between the nitrogen and the ring, but that arrow is telling us that we're going to take those electrons and create a double bond in the ring. And then the right side of the ring hasn't changed, so I can draw that in. And then this arrow, we're taking the double bond on that straight side of the ring and moving it down to the bottom part. And then last, I'm going to circle this in a different color. The one that I just circled in the other color, that's the loss of a leaving group. That chlorine is taking off. The electrons are going on to that chlorine, so that's showing us that it's the loss of a leaving group. And then what's left is that alcohol. So those other three arrows that are circled in blue are really just resonance arrows. They're showing that flow of electrons that we could explain through all of our resonance patterns. The one I circled in red is the loss of that leaving group, that chlorine that's taking off. Okay, one more example to add on here. And this is our, let me see where we were at. Okay.
I have a quick question.
Yeah.
Is the result of this always going to be a minus charged, like how bromine had ended with the minus charge and chlorine as well?
That's a good question. And the answer is no. So I will show you when it would be something that is neutral. It's either going to be negative or neutral. It won't never be positive.
Okay, thank you.
Okay, so this is where we were at with our example on the last slide. We're going to do a loss of a leaving group for this. So I'm going to do 2 arrows at once. This is my leaving group right there. We're going to kick off that OH group. So the bond, the electrons are going onto that oxygen to create our leaving group. And at the same time, we're going to do this. We're going to reform that double bond between the oxygen and the carbon. So we end up with that. All right, so let me show you. Do I have a, no, we'll just do it. Can just figure out where to do it. Let me show you where we would have a positively charged group that could turn into a neutral leaving group though. Actually, I know I have a blank slide. Let me just go back up a couple. Here, we'll do it here. So in kind of a similar example to what we were using, if we have an OH attached, but it is now an OH2, so it has an extra hydrogen attached to it, that can be our leaving group. We can reform that double bond. And we end up with H2O. This was our leaving group. So if our leaving group was positive to start with, it will be a neutral group in our solution at the end. And this is actually pretty common. Things that are negatively charged and stable that way, like halogens, are good leaving groups because we can kick them off. They can be negative, they can be fine. But there are things that aren't very good leaving groups, like having a negative OH isn't very stable. But if we add a hydrogen to it to start with and turn it into water, water is a really good leaving group. So we will often add hydrogens to things to make them into better leaving groups. And so we'll see that as we go through later reactions and later chapters. Would we be told what the leaving group is? So that is a great question. The question is, would we be told what the leaving group is? Yes, but it also kind of depends on what chapter we're in. So how things like this are going to show up on the test is 2 ways. Well, okay, 3 ways. Way number 1 is you would be given this, the structure and the arrows, and you have to figure out what the products are. So essentially, you need to understand what those arrows mean, bonds breaking, bonds forming, in order to show what gets created. So that would be problem type number 1. Where number 2 come from? Problem type number 2 you would be given this, and you would have to draw the arrows onto the reactant. So you know this is what you start with, you know this is what you're ending with. How do those bonds have to break and form to get to that point? So either filling in the products from arrows that are given, or filling in the arrows from products that are given. And then number 3, I'm going to skip slides here. Number 3 would be given this, arrows, reactants, products, and asked, what mechanism pattern is this? So you're either going to have to fill in the arrows, fill in the products, or fill in the mechanism type. I know that went beyond your question, but that's where we're at. You're welcome. Okay, so we did this. Questions about the leaving group? before we move on to type number 3? Okay, type number 3 is a proton transfer. So remember, when we say proton, that means a hydrogen. So sometimes these will be called proton transfers, sometimes hydrogen transfers. But when we're using the phrase proton, it means a positively charged hydrogen, because that's all a positively charged hydrogen is a proton. Doesn't have a neutron, doesn't have an electron. It's a proton. These are technically acid-base reactions because something is being a hydrogen donor, something is being a hydrogen acceptor. Even though they fall under that heading of acid-base, we don't normally think of them that way in organic chemistry because we aren't limiting ourselves to just using acids and bases. This one usually requires 2 arrows because we have to bond to the new hydrogen and we have to remove the hydrogen from whatever it was bonded to before. So this was the first example I showed you. And this is the only other type of mechanism we've looked at in a previous chapter. We're going to break it down into 2 subcategories though. And really this is just so that we can use this language, protonation and deprotonation. So protonation means that we're adding a hydrogen and deprotonation means we're removing a hydrogen. And we're adding or removing it to whatever the carbon base thing is. So in the first example, this arrow right here, we're going from the lone pair on the oxygen to that hydrogen. So that is showing the protonation. This arrow is forming the bond between the oxygen and the hydrogen. The other arrow is showing the bond breaking. So we're using hydronium, H3O+, really common hydrogen source for us. We're showing that bond breaking between that hydrogen and the oxygen. And then notice in our product over here, here's our new bond between our oxygen and our hydrogen. Now, technically, water is also a product because when this hydronium loses that hydrogen, we make water. Here's one of the things that you might hate in the start. We don't always draw in all the products. So I know you spend a chunk of time in general chemistry balancing equations. We don't even show all of our products in organic chemistry. We care about carbon, so we show what's happening to the carbon. Yeah, there's still water in there, but it was a reactant. It was part of what was aiding in the reaction to happen. We don't really care what happens to it. So this is our product that we care about. We don't really care about the water. And nearly everything we deal with reacts 1-to-1 ratio. So you spend all that time in general chemistry balancing equations and you end up with this like 5-to-2 ratio. And that does happen outside of organic. It is common in inorganic chemistry to have those crazy ratios. Organic is almost always a 1-to-1 ratio. The other half, the bottom half then, is deprotonation. So notice it's the exact same reactants we're looking at. We are now using water to remove a hydrogen. So this is going to form the bond between the water and the hydrogen. So this is going to make hydronium again. And then this is breaking the bond between the hydrogen and the oxygen. So the deprotonation step is this one, and the protonation step is this one. So whether we are adding or removing that hydrogen. And I'm going to add one more example over here in the corner. I'm going to go back. I'm going to continue with this reaction. So this is where we were at. To finish this reaction, we need to remove that hydrogen. We need to deprotonate this structure. So I'm going to use water to do that. I'm going to go from my lone pair on my oxygen Now notice I said I'm going from my lone pair on my oxygen, but I technically don't have any lone pairs drawn in there. That's okay. I'm going from the oxygen and it's understood that there's a lone pair there. I ended on the hydrogen, so that's forming my hydronium. And then I'm going to go from this bond onto that oxygen. So what we end up with is an ester, and we made hydronium in the process. Questions about those examples at all?
On the test, should we draw the hydronium since it is like not part of the carbon thing?
Yes. Yeah.
Okay.
And on the test question, I will put draw all of the products just kind of as a reminder. As we learn more, so I always feel like in order to know when you can kind of break the rules, you have to learn all of the rules really well. And we're still at the phase of learning the rules. So we would want to draw in everything else because we don't know when we can ignore it. We're not at that point yet. So yeah, you would want to include that. Good
Okay,
question.
thank you.
Okay, what? We're done in 5 minutes, right? Yeah, okay. So we have one more type of reaction. It falls under the rearrangement category. So we're going to talk about the very top of this slide and that's it, because the rearrangement one's a little bit more complicated. So I don't want to kind of get halfway into it. But what it's going to entail is looking at carbocation stability. When we have more carbon groups bonded to a positively charged carbon, it's going to be more stable. So we have a methyl carbocation, primary, secondary, and tertiary. So look at how we're defining whether it's primary, secondary, or tertiary. It's how many carbon groups are bonded to that carbocation. So if it has 1 carbon bonded to it, it's primary, 2 is secondary, and 3 is tertiary. Stability is increasing as we increase those groups. So I will remind you of this on Wednesday because we will talk about the Y. The Y is called hyperconjugation, which you might have talked about in general chemistry, but probably not. So we will start on this slide on Wednesday. We'll look at this reaction type, and then we will definitely do a bunch of examples and practice problems. But right now, we are going to switch over to lab. So I'll hang out here for the last couple minutes in case anyone has questions, but I will see you in lab Zoom in a few minutes.
Thank you.
Thank you. Did you say the study? Yes, the study guide is posted. So it's a couple spots. If you go into the modules section, or if you go into the modules and into the test module, I have it in there. And then if you go to just the weekly schedule link on the front page of Canvas, okay, you're welcome. It's linked there as well. I think I have it linked somewhere else, but yeah.
Hi.
Hi, Emma.
Sure. I'll just go ahead and go. I meant to join your office hours last Friday, but something came up. So
Okay.
I'm assuming you're still Thursday. I'm looking at your office hours right now. On Thursday, you'll have your office hour at 1 to 3.
Yes.
Okay. I really wanted to join because one thing that I didn't really even go into detail was the, let me pull it up. There was this one concept that I didn't really go into, and to be honest, I don't completely understand it. So I was hoping you could explain it a little bit